Good afternoon. My name is Don Tonti-Ploffel, and I'm the Associate Director of Academic Ventures and Engagement at Harvard Radcliffe Institute. It is my very special honor to welcome you to this exciting lecture and discussion in the Institute's Science Lecture Series, with our current emphasis at the intersection of food sustainability and climate change. At the start, let me acknowledge the members of the Radcliffe Institute Leadership Society and our annual donors tuned in this afternoon. Let me also specifically acknowledge the Mary E. and Clara Z. Costanza Fund for Science, which is supporting this event. Your generosity keeps Radcliffe programming free and open to the public. We thank you. Earlier this academic year, in October of 2023, we held our annual science symposium titled Feeding the Future, Food Sustainability and Climate Change. That symposium explored the dilemma, or seeming dilemma, of addressing the global climate crisis while feeding the world's population healthfully and equitably. I note in passing that a full recording of the symposium is available on the Radcliffe website. Now, that major symposium was a key component of our institute-wide and multidisciplinary climate change initiative, our omnibus effort to investigate the causes and consequences of the climate crisis, to develop strategies in adaptation and mitigation, and to address issues of climate justice in reflective thought and concrete action. We particularly seek to address the effects of the climate crisis on marginalized and vulnerable communities, both locally and globally. At the heart of this work is Radcliffe's commitment to supporting and sharing research that promotes innovative solutions and greater equity. This reflects Radcliffe's bedrock commitment to interdisciplinary study, informed by an equally deep dedication to inclusion. We firmly believe that these approaches will generate valuable new insights into effective and equitable ways of addressing climate change. In January and March, we held our first and second installments of this academic year's Science Lecture Series. Guided by Professor Jessica Fonzo of Columbia University, we explored the global connectedness that characterizes our food systems and the data complexities that unfortunately bewilder citizen and policymaker alike. With Swathi Viravalli of the National Security Council, we learn how the global challenge of the climate crisis motivates supra-regional dialogue and creates interesting new pathways for international cooperation. This afternoon, we build on those rich and encouraging conversations. Today's science lecture, titled Farming the Future, Livestock's Leap to Net Zero, to be delivered by our featured speaker, Professor Ermias Kebreab, brings into focus the Institute's priority on addressing climate change from the perspective of the most innovative developments in science and engineering. Contributing over 4% of global emissions, methane plays a significant role in warming our planet, with the livestock sector a major source. How can animal productivity be increased while aiming for absolute methane reduction? And how can the forces of industry and technology be marshaled in the pursuit of sustainable agricultural practices and net zero commitments? To help guide us, we will learn from Professor Ermias Kebreab, Sesnon Endowed Chair of Animal Science, Director of the World Food Center, and Associate Dean for Global Engagement in the College of Agricultural and Environmental Sciences at the University of California at Davis. Our speaker will be joined in discussion by our moderator, Professor Ido Berger, Faculty Co-Director of the Science Program at Harvard Radcliffe Institute, and Professor of Astronomy in the Faculty of Arts and Sciences at Harvard University. On behalf of Professors Kebreab and Berger, I encourage those here to use the Q&A feature on Zoom to submit questions at any time during the program. Please keep your questions concise so that we can explore as many topics as possible. It is now my pleasure to give the virtual floor to Professor Ermias Kebreab.
Thank you very much for the introduction. Okay, so it's my pleasure to come here today and to share with you some thoughts around the livestock and how do we get to net zero? How do we get reductions in emissions in the livestock sector? So let me begin by talking about methane. So what was the methane challenge? Methane is a powerful greenhouse gas and is the second largest contributor to climate warming after carbon dioxide. And the concentration of methane in the atmosphere has more than doubled over the past 200 years. And a molecule of methane traps more heat than a molecule of carbon dioxide by 82 times over 20 years and about 28 times over a 100-year period. And it estimated that methane is responsible for half a degree of climate warming since the Industrial Revolution. But methane is short-lived, about 12 years or so. And cutting methane now is the quickest way we have to slow global warming. And about 30% reduction now by 2040 can help us avoid about 0.3 centigrade warming by mid-century and about 0.5 by 2100. So where does methane come from? What are the sources? Well, there are both anthropogenic sources and natural sources. So the natural processes account for about 40% of the emissions, with wetlands being the largest natural source, mainly because for methane that there needs to be anaerobic environment, and wetlands are perfect for that. But estimated 60% of today's methane emissions are the result of human activities. The largest source of methane are from agriculture, fossil fuels, and decomposition of landfill waste. However, there is actually massive underreporting going on of methane emissions. Landfills, and in some cases, are underreported by a factor of 200%, oil and gas by a factor of 5. Recently, Germany reported emissions from coal to be 184 times less than actually was. In terms of agriculture, we kind of fairly know, if you know how much they're eating, if you know what they're eating, and the number of animals, you can fairly estimate how much methane is expected from the animals. So looking at the contributions within the agriculture, enteric fermentation is a major source, which is followed by manure management and rice production. So today, I'm really focused on enteric fermentation, as I said, because it has a huge impact on methane emissions and therefore on greenhouse gas emissions. So the FAO broke down the pathways to low emission future for livestock systems. This was featured in COP28 very recently. And there are both demand side and supply side reduction that can happen. And when they estimated from the demand side is basically reducing consumption of animal source food, so dietary changes. And if they're fully adopted, they estimate that there'll be 6% reduction in greenhouse gas emissions. But if you look at the supply side, up to 70% of reductions can be achieved through the supply side. So I'm more focused today on the supply side because that's the work that I'm more familiar with, and that's the work that we're doing at Davis and around the world as well. And so we conducted a series of meta-analysis to quantify the impact of adopting various mitigation practices on global temperature. We estimated that reasonably adopting practices can help us meet the Paris Agreement target only until about 2030, but we will need further reductions by 2050. And this is really active field, and there have been a lot of progress since we conducted this meta-analysis, which I'm going to share with you today. We're looking for technologies that can widely be adopted, that can give us a considerable reduction in methane emissions. And there are a number of those that have already been identified that you can see on the slide here, and different groupings. But I'm going to focus more on the last one, which is the rumen manipulation, and particularly I'm focusing on the feed additives as well. Feed additives are ingredients that are given in small quantities that have impact in either inhibiting methanogenesis directly or indirectly through modifying the rumen or gut environment. And when it comes to efficacy, it's very clear that bromoform containing seaweed or halogenated compounds containing seaweed seem to have the largest reduction, followed by fatty acids or lipids. And compounds such as 3-nitroxypropanol, or known as bovire in Europe, have also shown a reliable reduction in emissions. We've seen also a number of compounds that are plant secondary compounds. They may be effective, but their effectiveness depends on several factors. So I'm going to talk a little bit more in detail on the things like seaweed and others that have huge promise in in the future. So the microalgae or seaweed Asparagopsis taxiformis has been widely studied all over the world now. It has shown effectiveness ranging anywhere from 30% to up to 98% reduction in mitigating enteric methane emissions. The active ingredient here is halogenated compound bromoform, and once consumed, 90% of the bromoform breaks down to dibromomethane within about 3 hours, which is then further degraded through other methods, particularly the cofactor F430 mediated process. And this process catalyzes the last step in methanogenesis. So that's what this disrupting. And we did an experiment at Davis. One of the first experiments that was done was here at Davis in dairy cattle, and we supplemented the seaweed at small levels at 0.5% and 1%. In this particular time, we didn't actually know how much was going to be effective because nobody has done it before. In vitro, it showed up to 2% reduces complete reduction in emissions, but in vivo, we didn't have an idea. So we have to start from slowly, and then we went up to 1%, and we saw about 67% reduction. But the issue was that palatability was also compromised. So at 1% level, the cows didn't really eat as much as we would like them. And that's because the taste is different. They're not used to it. Just like people, if they're used to something, they will eat it. But if they're not used to it, they won't. So at 1%, we were struggling a little bit. But then we modified the diet, and we did a second experiment where in beef, we reduced the highest concentration to be at 0.5% level. And then when we did this, we saw, again, a substantial reduction. We saw up to 80% reduction of emissions here. And this is a much longer period of time also. We did it for about 5 months. So we didn't see any kind of evidence that microbes were adapting to it. And there were some differences depending on the diet. So you might ask the question where up to 12 weeks, the control was higher. And then after that, even the control was reduced. And that's because we changed the diet. In a normal beef production system, what you do is you have high forage at the beginning and then high concentrate at the end. And high concentrate is usually associated with less methane because it's more degradable. So this is what we're expecting in terms of the control. But then we've seen quite a big reduction in emissions, as I said, up to 80% when we added up to 0.5% of the seaweed. So feed additives, by their nature, you have to supplement them on a daily basis. And so this works fine if the animals are, if it is dairy where you need to milk the animals on a daily basis, or if it's a feedlot where you feed concentrate, this works absolutely fine. But the majority of animals are out in the pasture. So we wanted to do some experiment, grazing experiment, where animals were supplemented with this microalgae. And this will work in winter months, in colder climes, when animals need to be supplemented because the ground is frozen from maybe October to about now or in April. And so there needs to be supplementation. So we can add this as a supplement. And so this is the work that we've done in Montana, one of the largest ranches in the country. And what we've seen is that although the average reduction was about 40%, it varied very depending on how much the additive the animals were consuming. So what we saw was that as long as the animals are consuming the additive, we see a huge reduction, some cases up to 80% reduction. But this is entirely voluntary. And so when animals feel like it and they go in and feed from it, then we see quite a big reduction. If not, then we don't see that much reduction. And as the time goes by, there's less and less of it been consumed. So there's still some issues of palatability there, but this is more work has been done to make it a lot easier, much more palatable. And some of the popular ones that people are looking into right now are infusing it into oil. So you basically take out the active ingredient in oil so that there is no other added stuff that's probably contributing to the palatability issue. So if that happens, then you would see an uptake and then a reduction in emissions. And the other thing that we wanted to make sure is that we don't compromise productivity, because if you reduce productivity, then it's not going to be, you cannot expect farmers to adopt this. From this graph, it's clear that at least we did not drop any productivity. There's a potential to increase productivity because methane is energy source. So if you reduce the energy source, then more of that energy could potentially be kept within the animal, and therefore you can increase productivity as well. But we needed to have a lot more animals to be able to quantify those impacts. In the first long-term study using a methane inhibitor called the Bovire or a 3-OP, there was a report about 20% reduction over entire lactation. So up to this point, a lot of the work that has been done were more 3 to 4 months in duration. And within 3 to 4 months, you see maybe 30% reduction for this particular additive, for example. But there was always a worry, if you feed it continuously as you would do in any livestock operation, what would happen? And so this is the first evidence that we've seen that over a long period of time, it still sustains that reduction, about 20% reduction. And at the same time, there was also a report that an improvement of 6.5% in productivity as well. So increase in productivity, reduction in methane, seems to be a win-win kind of situation, win for the farmers, win for the environment, and good for the customers as well. So further on, then we looked at about more circularity of nutrients. So now we're talking about the feed additives, and then the next thing that I wanted to bring up is if we include more of the byproducts that have been produced, then we could also help in reducing emissions and become more efficient in utilizing the resources that we have. In California, the two biggest industries are the wine industry and the dairy industry that are very close geographically, that are quite close. And wineries have huge amount of byproducts as grape pomace. And grape pomace is rich in tannins and polyphenols and lipids. And there's some evidence that tannins help reduce methane emissions and may also improve milk quality. So we teamed up with the food science department here in Davis, and we conducted an experiment looking at adding grape pomace into this feed. So this is unprocessed grape pomace. We literally went with a truck to Gallo Winery, which is about a 45-minute drive from UC Davis. And we brought in those grape pomace. First, we did analysis in terms of the tannins and polyphenols and all that. And we selected the variety of the grape that have higher tannins, and we included about at 10% and 15% levels. And what we found was that the 10% and 15% were about 10 to 11% reduction in emissions. And what is even good is that not only do we reduce emissions, but also we've seen an improvement in milk quality. So we've seen the polyunsaturated fatty acid levels were increased with pomace supplementation. And even better, what we saw was the feed efficiency also increased. And so in this case, the animals ate a little bit lower, but they produced more milk. In terms of palatability, the animals absolutely loved it. So both at 10% and 15%, there was no issue in terms of palatability, but in general, they consumed a little bit less than the control cows, but then the milk production was a little bit higher than the control cows. So there's a better feed efficiency, which means economically also better for the farmers, and it's also better for the environment and better for consumers because now we've seen milk quality improvements as well. So we might do a couple more experiments to make sure that there are no unintended consequences, and then hopefully this is one of the things that dairy farmers in California and elsewhere where grape pomace is available can adopt and be part of that cycle. Already in California, about 50% or more of the feed to lactating dairy cows is byproducts like almond hulls and cottonseed and things like that. So this will even further improve the amount of byproducts we use for lactating dairy cows. There is evidence that showed a high genetic correlation with heritability of about 0.3 for mean weekly emissions. So basically, methane emission is moderately heritable. So now I'm moving on from the feed additives and byproducts into genetic selection to reduce methane emissions. And we assembled a data set of dairy cows of all experiments that were being conducted after the year 2000. And what we found was that an average of 20 gram of methane per kilogram of dry matter intake, or the amount they're consuming, is what we expect for the emissions to be on average. But there was a variability. So that variability was between 2.1 to 2.7 gram of methane per kilogram of what they were consuming, which means that through selective breeding, we can actually then able to lower that emission by a factor between 2.1 to 2.7 gram of methane. Compared to nutritional strategies, genetic solutions result in long-term progress, and therefore they tend to be more cost-effective over time. And research with sheep in New Zealand showed a 12% reduction in emissions through breeding, the breeding of the sheep. So they actually have now a breed of sheep that would have 12% methane lower than so what you would expect to be the normal sheep. The same thing is happening. The same kind of work is happening in dairy cattle, also in Ireland, in Canada, and the US. And preliminary results have shown that breeding animals for reduced methane emissions could actually end up reducing emissions by about 11 to 26%. Now, this is what I'm really, really excited about. So very recently, we got a $70 million grant to work with UC Berkeley and UC San Francisco, and to work on engineering microbes, using CRISPR to engineer microbes so that we can use it to reduce methane emissions as well as for health as well. So for UC Davis, it's mostly on the methane front. So what we're doing with this is that the truly enabling technology for this effort is the CRISPR-Cas systems as revolutionary genome editing tools. And over the last couple of years, the Berkeley team have taken these tools and developed them into a generalizable tool set for microbial community editing. As a first step, this framework, DNA sequencing-based approach that was developed at UC Berkeley, will be used to determine what microbes we can edit within a community and which tools can be leveraged to do it. And in the second step of this approach, a new CRISPR-Cas variant will be used to make targeted edits in the genome of the strain we want to edit in that community. And this work actually represents the first generalizable tool set for engineering the DNA of microbes. So what if you could instead precisely control the DNA of microbes? It will allow suppression of methane emissions by microbiome by targeting the pieces of DNA that are causing methanogenesis. And DNA editing would be conducted to promote competitors of methane-producing bacteria or hydrogen-utilizing microbes. So what happens when you reduce methane emissions is that there will be more hydrogen being produced. You see a lot of hydrogen being emitted out, which is not really great. And hydrogen is also a source of energy. So there's a potentially, we can upregulate the bacteria that can utilize hydrogen so that there will be better productivity as well. So we are just about to start this work. In fact, this morning we received the IACUP protocol approval, which means we can start the in vivo work, and we're going to starting from calves all the way to adult animals, and doing a longitudinal study to understand the microbiome development and figuring out which microbes are responsible for what, and then under what conditions can the microbiome be stable even if we reduce methanogenesis through genetic engineering. So, this is well and good, but the majority of methane emissions, about 70% of emissions, comes from production systems that yield less than 2,000 kilograms of milk per year. So this is in milk production, but also in the meat and other production systems. The emissions intensity is very much correlated with the productivity. And these are also countries where we would expect an increase in demand for animal source food. So instead of adding more animals to meet that demand, what we're trying to do is to have more productive animals, so that per kilogram of meat or milk they're producing, you have much less methane emissions. We've done that in the US, for example, over the last 50 years, per kilogram of milk we're producing, and there's 45% reduction in emissions. So this is the sort of the way that we're trying to go. And the way we do it is by developing a ration formulation tool to provide some guidance on what and how much to feed animals and these particular production systems. One of the things that we're doing is we are developing a simple tool that allow to estimate nutrient contents of the feed. So one of the things you need to know, to have a better productivity is you need to know what's the requirement of the animal and what's the ingredient that we have, what's the nutrition composition of the nutrient that we have. And so in a lot of low-income countries, this is really not non-existent. So we are working in about 13 countries right now to try to develop a mobile device-based app just to measure the nutrient content of the feed that's available in the country. We're developing a nutrient requirement for the dairy cattle of that specific species because they are different from Holsteins that we used to here in the US. And then putting all that together and deliver it through a chatbot. So developing a chatbot so that farmers don't have to go through the installation and running of a software and all that kind of stuff. So basically, you will have your mobile device and you will type in, this is what I have. You point the ingredient that you have, it will upload it, and then you will select the animal that you have, and then it will also upload the requirement, and then it will match the requirement with ingredients, and it will tell you need to feed X amount of corn or this and this and that, or pasture and this and that, and that will give you a guidance of how much you need to feed in order to get a certain level of productivity. And this is also will be done in the language that the farmer or farm advisor is using, because one of the biggest bottlenecks has been that those systems were not available in different languages. So now through the use of AI, it will be automatically translated and be available for people to use. So, and in conclusion, then, to help us get closer to a net zero livestock production, we need to have multiple approaches as appropriate. And this include feed additives in housed animals, circularity of nutrients using byproducts and genetic selection, engineering microbes to reduce or may even eliminate methanogenesis, and also improving productivity. Just finally, I'd like to acknowledge the support of various organizations, federal, state, industry, and philanthropic sources that have contributed to this work, and of course, my team who has been doing the lion's share of the work. And that's it. So I will now bring Professor Berger to the virtual floor to join me in the conversation and pose audience questions.
Thank you so much, Ermias, for the enlightening presentation on such a fascinating and critical topic. So I would now like to follow up on your presentation with some prepared questions, and we've had quite a few questions coming in from the audience online. So I'm going to try to weave these questions together and follow some themes. Hopefully we'll have time to address all of them. As a reminder to the audience, you can continue to submit questions using the Q&A function, and please keep them concise so we can get to as many of them as possible in the time we have. So let me start with taking a step back. You mentioned that about 60% of methane emissions are anthropogenic, and a large fraction of that comes from livestock. And I was wondering if you can tell us a bit more about the kind of the breakdown between emissions that are due to cattle, dairy versus meat, as well as other livestock, pigs or sheep or goats, and et cetera.
Yeah, sure. So the majority of the emissions are from ruminants because of the specialized digestive system they have. So the enteric emissions that I was mentioning, about 25%, that was all sort of belching out from the rumen, and that is all dairy cattle and beef cattle, to a small extent sheep and goats as well. But they don't consume as much feed material as a beef cattle or dairy cattle. And I would say maybe about 70% of that is from beef cattle, just because the number of the beef cattle is much, much bigger than dairy. In the US, for example, we have like 9 million dairy cattle and 90 million beef cattle. So although each dairy animal would consume, let's say, 25 kilogram of dry matter per day, beef and about 10 kilogram, but there are so much more of them. So a lot of the emissions is coming from that. And then the manure also contributes to a lesser extent, and depending where you are. So the manure, if it is managed in a lagoon, like it is done in a dairy system, there's much more emission happening because it's anaerobic, and there will be emissions. And also depending where you are, like in California, where it's hot, then you will have more emissions, while in Minnesota, it probably be less because half of the year would be too cold for methanogenesis to happen. So the pigs and poultry, it's mostly from manure. In swine systems, a lot of the manure is being handled as liquid manure in a lagoon. So that's the emissions that are coming from that. And so the manure is about 9%. So that's kind of the breakdown. The biggest part is the enteric fermentation. That's why I focused a lot of my time today talking about enteric. But there are solutions for manure also. Particularly anaerobic digesters are the big ones now in California. We have now over 200 been built over the last 10 years, and they seem to work quite well. And you have renewable energy and a number of other factors that would help and make this work well as well.
Yeah. It's interesting that you bring up the digesters. I have a question about that I'm going to come back to in a minute.
Yeah.
Another question related to the manure management side of this. So you mentioned that the enteric emissions are likely estimated correctly, but some emissions in other sectors are maybe underestimated by large amounts.
Yes.
Do you know that the contribution from manure management is correctly estimated, or is there a possibility that that's heavily underestimated?
Yes, I think one of the issues for sure in terms of estimating manure management is quite difficult because it's in a diverse area, and it's not as well understood as enteric fermentation. I think for enteric we have done a lot of measurements for a long period of time, so we fairly know well emissions. But from manure, there's a number of factors. You have factors in terms of how much solid or organic matter is in that space, and how it is stored, and for how long it is stored. All of this, the carbon nitrogen ratio, all of that will have an impact on that. So yeah, I think estimating emissions from manure is definitely one that we really need to invest more and try to understand more. So the IPCC has some values, standard values, but I think those values need to be updated. I think they're so much different depending on the temperature and then with climate change, with increasing temperatures, then you're going to have more impact as well. So yeah, I agree. I think the measurements or estimations that we have from manure is a lot less precise than we do from enteric.
So let's go back to these digesters in California. So it seems like the state of California has provided financial incentives for dairy to use these digesters, and then to harvest the methane and use it for generating electricity and fueling trucks and so on.
Yeah.
And the estimates I've seen is that has led to a reduction of about 20% of the needed emission reductions.
Yes.
Which is great. But then this approach has been criticized for increasing the presence of ammonia, which can then lead to pollutants and fine particulates that can affect air quality. And so I'm kind of wondering about this balancing act between reducing kind of the global impact of methane emissions, but potentially having unintended local adverse effects in the communities nearby these farms.
Yeah, I think that's a very good question. I think there's a lot of trade-offs that's happening and a lot of mitigation strategies that you can come up with, and this is one of them, where you may have a more sort of nitrogen-based emissions happening, and you're reducing methane by quite a bit in some cases. But I think this is a call for more research to see how we can sort of clean up the digesters so there's not as much ammonia coming out from those digesters. So I think with further research, and the state of California is investing a lot of money into this issue at the moment. So I think with further research, we need to focus our attention and making sure that those unintended consequences are being addressed. And the same thing as I was talking about methane, for example, you reduce enteric methane, but then you increase hydrogen coming out from the animals as well. And hydrogen may not be as bad as methane, but still has an impact on the environment as well. So how do we deal with that? And there's more research that's happening right now. There could be some things that you can feed together that would allow the microbes to utilize hydrogen and keep it in the stomach as well. So yeah, so my response is I think we need more investment in that area to be able to reduce those unintended consequences.
So I'm wondering now about the geographical distribution of, I mean, you mentioned California, and that's what you do a lot of work, but what is the kind of the geographical distribution of methane production from livestock? Presumably it's not uniform across the whole country. So are there specific states that are responsible for most of the methane emissions from livestock? And we'll come back later and talk a little bit about, differences in regulations between different states and how that feeds.
Yeah, so I think the states that have a higher concentration of livestock would, particularly ruminants, would be the ones that would have a higher amount of the emissions. So if you come to dairy, the number one state in terms of dairy production is California. So about 1.8 million dairy cattle currently in the state. So you have California, Wisconsin, Idaho, and New York and Texas probably are the top 5 states that have a higher amount of dairy cattle. And then beef cattle, you can go all the way from Texas to through Oklahoma, Nebraska, and all of that is where a lot of the cattle are. And so those are the states who will also have a higher concentration of at least enteric methane emissions happening as well. Yeah, and then from manure, places like Iowa, where we have a lot of swine production and a lot of the manure being in lagoons, they will have also, when you compare with other states, a greater amount of emissions coming from those spaces as well. And I guess that's one of the reasons in California we see a lot of regulations coming in to reduce emissions. We have the SB 1383 right now to try to reduce methane emissions by 40% by 2030. As you mentioned earlier, through the manure management, particularly from anaerobic digesters and other types, the state has gone down to, well, it's projected by 2030, 20% reduction in emissions, but we needed 40. So that other 20% has to come from enteric. So if you look at that until 2030, we can't get there with manure. We need the enteric aspects. So the 20% need to be included by enteric. And one of the things that really frustrates me is that we still don't have an approved feed additive, although a lot of work has been done, has been shown that to work quite effectively, and other places have already approved those feed additives.
Great. So I was wondering, I wanted to get your thoughts on tracking methane emission. And a few months ago, MethaneSat was launched.
Mm-hmm. Mm-hmm.
And it's a collaboration between the Environmental Defense Fund and, for example, Harvard University, amongst others.
Yeah.
And the idea is to track kind of real-time emission of methanes, covering areas that produce most of the methane in the world, and making the data public to enable accountability and action. Do you think this is going to be useful in the context of livestock and agricultural management, or do you think that's more aimed at natural gas production or things like that?
Yeah, I think when you have kind of a point source like the natural gas production, those could be a lot more effective. It just depends on what is the sort of the gradient that the satellite is looking at. So I think definitely it's a move in the right direction. So one of the things that's critically missing in this space is reliable measurement, from a farm, for example. So if you're going to do all this mitigation I was talking about, how do you measure and to see that you have actually achieved your goal? So one of the things that we're trying to do with Caltech and Stanford and others is to work with NASA to have a similar satellite, but much more sort of at a finer point, so that you can look at individual farms and try to understand what's the emission coming from the farm, both from the housing animals that are in the house, but also from the manure as well. And so that when you make those interventions, you can actually then measure and say, yes, we have achieved what we intended to do. Because we can do a lot of stuff in a controlled environment, but when it comes to actual farm and deploying those technologies in the actual farm, it may not be the same, because we're feeding them. We know exactly to the gram how much the animal is consuming, while in a big operation, when you have 10,000 or more animals, you're not going to have that finer control. So you're going to have to rely on satellite in this case, or some sort of technologies where you could cover the whole farm and see what level of reduction is achieved from the whole farm. But I think the methane side, that's very exciting. I'm looking forward to seeing some of the data. I think some of the earliest stuff that we've seen, there were some concentrated animal feeding operations where the methane levels were quite distinctly higher than the surrounding areas.
Okay, so I want to switch gears a little bit and talk about the the feed and additives that you mentioned. So you gave several examples of things that seem to be helpful and that can work. And I'm wondering about adding that on, bringing it up to scale. Are there any issues with regulations that are standing in the way, or how are regulations in the US, for example, compared to what you see in other countries?
Yeah, so I think the regulation that's happening in the US is well, it's quite different, and in a way, because all of those feed additives have to go through FDA, and FDA basically looks at those that reduce methane emissions as drugs. And so you can go to a food route and you can go to a drug route. And the drug route, as it should be, is very complex and a lot of work that needs to be done, and lengthy as well. While the food way is much more easier, or at least it's not onerous to go through that. So at the moment, anything, if you want to claim it reduces methane emissions, it has to go through the drug route, which means a lot more expense and much more time to get to that. But if you look at it, a lot of the issues or the additives that are being developed, they don't really change a lot with how the animal works. They're not really drugs. They're food additives, and that's how they've been labeled in the EU, for example. The European Union have approved 3-NOP and others, and so they're looked as a feed additive with environmental benefit. Canada 2 months ago approved it as well as a food additive, but in the US we're still struggling with this. There has been 2 bills introduced, one in the House and one in the Senate, to kind of to create a different pathway for feed additives. So I think the FDA needs a congressional mandate to be able to create this pathway so that it can go through this. And I think there is some movement happening in that direction at the moment. And the FDA very recently said that they intend to withdraw going through the drug route. So there's the intent. I don't know when it's going to be implemented, but at least there is a realization that things have to change. Otherwise, in the US, you're going to be left behind. A lot of those feed additives have been shown to work quite well, and a lot of studies have been done. So I think there has to be a much easier pathway to get the feed additives approval. I mean, they have to be definitely make sure that environmentally and for animal health purposes and for consumer health purposes, make sure that they are safe. But there has to be a clear pathway to do that, so that people who are developing those know exactly what's expected of them and they can do it that way.
So there were quite a few questions that came in about the grape pumice and tannins. There's a lot of that. So I'll try to kind of summarize. There are kind of several aspects to this, but one question was about scalability. And so, is there enough of this to make an impact? And also, whether there are other sources of tannins not from grapes in other parts of the world where that might be used kind of more as a local intervention. And also whether there is a need to kind of incentivize the wine industry in California to participate in this, or is this kind of a win-win and it works for everybody?
Yeah, no, I must say the wine industry were very much in support of this of the work that we're doing. In fact, in places like Australia, where it's also another wine with a large wine industry, this is becoming almost a standard practice. So I think there has to be a closer relationship in terms of the use of byproduct between the wine industry and the dairy industry. I think incentives always help. I mean, we've seen it in California because of incentives. We've achieved a lot of reductions. So yeah, incentives would be good, and it's also a great thing for winemaking. I mean, they can become more sustainable by using the byproduct that they don't really use anymore, right? So we can only compost so much. There's a lot of grape pomace that's been produced in the state, and we have, as I said, 1.8 million cows. So there is a ready market there, and the byproduct is already there as well. And there's minimal processing required, and they're geographically collocated. So I think it just makes sense to be able to use from one industry to the other. And then in the broader question of tannins, yes, there are a number of other plants that have tannins. For example, lemongrass. So we've seen lemongrass that has higher concentration of tannins that also help reduce methane emissions as well. But you have to make sure that there is enough tannin concentration, because when our collaborators did it in Mexico, it worked well. When we did it in California, it didn't work as well, because the California variety, because it's a temperate variety, did not have enough tannins and polyphenols to actually make a difference. So as long as there is enough tannins in those kind of plants, then we'll see differences in emissions. And in a lot of tropical countries, a lot of plants will have those secondary plant compounds, tannins and others for defense mechanism for the plant, but they are also good for reducing methane emissions as well. So yeah, it's applicable worldwide in different sources of tannins all over the world.
Kind of related to this, so there are these, you mentioned these genetic variations in the feed itself, potentially from one place to the other, which gives an opportunity to kind of tailor the solution locally. There are also, I guess, genetic variations in cattle from one place to the other, and so is there an effort to kind of match these things, or are we going to need to push on, you talked about selective breeding and so on, but kind of go in and genetically adapt livestock to match the local resources and the kind of the best approaches to reducing methane emissions?
Yeah, so what's been happening, over the last few decades is breeding. You put value to it. So what's the value? For example, most of the time is productivity, right? So a lot of the breeding you do is you put a huge emphasis on productivity. But what we see now is that you can actually include things like reduced methane emissions as part of that breeding value, so that when you're breeding animals, when you come up with new breeds, you have animals that are inherently would have lower emissions than their fathers or grandfathers. So we see that more and more happening, and we see in livestock intensive countries like in New Zealand, for example. This has been going on for the last few years. I think over the last 10 years they have achieved about 12% reduction in sheep, and in places like Ireland, where there is a relatively large amount of dairy cattle there, they're doing the same thing. In Canada, the same thing, with a fairly large dairy population. And so I think there is the realization that we can do multiple things to come up to a more sustainable livestock production. So genetic selection is one of the things. So we do genetic selection anyway. I mean, it's every year you will see about 1 to 2% improvement in milk production. That's because of genetic selection. So now what people are doing is they're including the emissions aspect into the breeding value, so that every year you will see animals that have lower and lower methane emissions. So over 10 years, 15 years, you come up with a breed of animals that are, compared to now, maybe 15, 20% lower reductions, and that's permanent, right? So once you are into that level, it's a permanent reduction that you're gaining, and it's great for animals in pasture because you don't have to supplement anything; it's already in their genes, and so that way you can achieve a really a big reduction over many animals.
There are also quite a few questions related to costs. So
yeah.
Some of these solutions, requiring these additives or genetic modification using CRISPR and so on. Those are not presumably cheap technologies, and so how is that, or what's the best way to handle that to make this financially sustainable, and not just in a wealthy country like the US, but globally?
Yeah, so there are different ways in which to achieve this, and one, for example, is the carbon markets. So there is carbon markets have been developed so that when you're using those additives, those different technologies, and you're reducing methane emissions or carbon emissions in general, you can be compensated for that, or you can be able to sell that carbon. We already have a carbon market in a regulatory carbon market in California, but there's also a voluntary carbon market that's been developed as well. So I think that's one way to do that. And second is that a lot of the big companies that are using animal sources have already pledged to get to net zero by 2030, 2040, 2050, depending on which one. And so they have a financial incentive for them to show the shareholders, we are getting to net zero. And one way of doing that, a big way of doing that, is to use those feed additives and provide them to their suppliers so that they can get them, they can get that reduction. Because most of the reduction, I'll say 70, 80% of the emissions for large companies like Danone or Starbucks or something, it's the milk or the meat that they're buying. And so if they can source it from a way in which the farmers have reduced emissions, then that carbon could also they can get that credit so that they can show that they're getting closer to the net zero, or to what they have promised to do. And the third way is creating value for the product as well. So you go to the supermarket and you can see some with a lower carbon footprint may be more attractive than the ones that are done in the traditional way. So you can add value to that as well. So different ways of achieving that. And then for the low-income countries, I think additives that improve productivity, not just reduce emissions, but productivity as well, could help at least pay for themselves at the very least, but hopefully also be beneficial to the farmers as well.
So I want to follow up on a statement you just made, which is the ability of consumers to kind of to track and make choices about consuming dairy or meat from farms that use methane mitigation approaches. Is that information that's available currently, or is this something that's envisioned for the future? What?
In Europe, when I travel to Europe, I see a lot of countries actually write the carbon footprint of all the products that you're consuming. But I haven't seen that much in the US. But I think when the carbon market develops, we probably see, I think when those companies want to differentiate their products, they probably start adding those numbers as well, so that consumers are better informed and see what's the cost in terms of the environmental cost of consuming certain products.
We have a question from the audience also about getting all of these approaches up to scale and up to speed. And so I guess the question is kind of what is the bottleneck at the present? Is it more about the kind of the research side of it and trying to find out what kind of feeds work, what kind of selective breeding works? Is it adoption of things that are already there but maybe not incentivized, or is it just federal investments? What do you think, Aaron?
So I think there are sort of 2 or 3 different levels. One is that there is the research that we already know, but needs to have data on consumer safety as well as animal safety. So those are the things that could be scaled up very quickly, but you need to do multiple experiments at the same time. And now we do have things like the Global Methane Hub, which is really set up to accelerate this. So they actually have something called the accelerator, where they will try to push those things out as quickly as possible, because you need to have multiple experiments at multiple sites to make sure that it's happening. So that's where the things, when you've done a lot of the basic work and you're kind of more or less satisfied that this is working, then you can go to that level. And then you have at the one level below that is when you're trying to understand how things are working. What's been happening is that, one person does this, one institution does this, publishes, and then another institution takes that up and then publishes, and then it takes a long time to do that. But if you are able to try to understand different aspects of this same thing, then at different locations, you can also very quickly build up that knowledge, and then you move to deployment. And then there's also at the basic science level. That also needs to happen. This stuff that we're doing with the microbial engineering, for example, is right now is really basic sort of science level, where we're trying to understand about the microbiome development and to understand the genes that are responsible for methanogenesis and all that. And then the second level would go then having this editing tools and have edits and making sure that there's no unintended consequence. And then the third level is going to the animal themselves and then doing animal experiments where we see the reduction. So, I mean, there's multiple things going on. And I think I saw something about the vaccines, so vaccines are going to be a really great way of reducing emissions, because then, a lot of animals are being vaccinated anyway. And so if you add one more vaccine into it and be able to come up even with about 20% reduction, this will make a big change as well.
That's great. I think we have time for one final question. So I wanted to bring up, there was an article last week, I think in the New York Times, talking about efforts in the Amazon to reclaim cattle grazing land for reforestation, with the idea that what was claimed is that there's a report by Bloomberg saying that the carbon markets could be valued by 2037 at about $1 trillion, which is double what the global beef market is worth. So the idea is that maybe the land will actually be more profitable forested rather than for used for cattle grazing and selling carbon credits. And so I was wondering what your thoughts are on these kind of efforts, and do you think that?
Yeah. I mean, this is slightly outside of my my area of expertise, but what I understand is that a lot of the beef production is happening on marginal lands. Those marginal lands, I don't think it's possible to have reforestation happening on those marginal lands. To begin with, you can only what you can do is really manage the grass. They're grasslands from many years. They are basically the grasslands, and that's their natural sort of state. And so I think maintaining those grasslands and having more carbon sequestration happening probably would be more beneficial than having new creation of a new habitat. But I mean, as I said, this is not really my area of expertise, but I've been very impressed to see some methods in which it's really learning from nature, having things like mob grazing, where you bring in animals and you really graze, and you have all the manures going in there and trampled in, and then you move on to the new fresh, and that way you can really replicate what nature has been doing for millions of years with bisons and other ruminants. I think that kind of production system will increase the soil carbon quite a bit, so you have more carbon sequestration happening in those fields.
Well, I think we can probably go on for another hour and a half with a lot of questions that are coming in, but unfortunately we're at time. So I really want to thank you, Ermias, for joining us today and for the illuminating conversation. This concludes our program today. I want to thank Professor Ermias Kebreab for his excellent presentation and our conversation, and our audience for the terrific questions. Today's program has been recorded and will be posted on the Radcliffe website in about a week. For information about upcoming Radcliffe programs and to see videos of past events, please visit radcliffe.harvard.edu. Thank you again for joining us today, and take care.